Hello, my name is Edward Lee. It's a real honor to be here at the technical conference PREVAIL in 2021. I'm going to be talking about determinism. A little bit about me. I'm a professor at Berkeley. I've been at Berkeley for some 40 years, and I work in the area of cyber-physical systems, which are systems that combine computation, networking, and physical subsystems, such as self-driving cars, industrial automation, that kind of thing. So throughout my career, I've been pretty obsessed with determinism, and I'm a little bit embarrassed to admit that I only really relatively recently feel like I am coming to understand the problem. So a couple of references, if you want just a short read. I published a blog on this subject in the SIGBED blog. I also published a paper in the ACM Transactions on Embedded Computing Systems. You can see these references here. I've also published 2 books, which are my attempt to speak to a general audience, and determinism is one of the topics that is addressed in these books. Determinism also figures fairly prominently in technical books that I've published, including my Introduction to Embedded Systems, co-authored with Sanjit Seshia, and a book on the Ptolemy system, which it was a long-term project in my group to build deterministic concurrency into software systems. So, what is determinism? Well, in physics and philosophy, it really means that every action is a consequence of preconditions and fixed rules. The preconditions cause the consequences, and as a result, the notion of causation is integrally tied with the notion of determinism. Many people have a distaste for non-determinism in the physical world, and we try to find deterministic mechanisms in our models of the physical world. And I think that the distaste for non-determinism in the physical world follows from a distaste for uncaused action. But the notion of causation is actually not so trivial. In fact, Bertrand Russell famously in 1913 challenged the scientific community, claiming that in fact causation has no fundamental role in physics. In this rather colorful quote, he says, "All philosophers of every school imagine causation is one of the fundamental axioms or postulates of science. Yet, oddly enough, in advanced sciences such as gravitational astronomy, the word cause never occurs." The law of causality, I believe, like much of what passes muster among philosophers, is a relic of a bygone age, surviving like the monarchy only because it is erroneously supposed to do no harm. So many philosophers and thinkers have followed up on this and questioned the notion of causation. Some evolutionary biologists believe that that the notion of causation is one that evolved because of its fitness value in a Darwinian evolutionary system, and that it's not actually fundamental in the physical world. So this questioning of the notion of causation and its integral tie with determinism makes the concept of determinism rather difficult to reason about. John Earman, in a very well-cited book that is perhaps one of the best references on determinism, admits in the preface to the book that it's an extremely difficult subject, and he says, "This is already enough to make a strong suspicion that a real understanding of determinism cannot be achieved without simultaneously constructing a comprehensive philosophy of science. Since I have no such comprehensive view to offer, I approach the task I have set to myself with humility, and also with the cowardly resolve to issue disclaimers whenever the going gets too rough." So one way to think about determinism is that it's about the resolution of alternatives. If a system in the physical world can evolve in more than one way, the question is, how is the way chosen? When is the way chosen? And why is that particular way chosen? So these are actually 3 different questions: the when, how, and why. And let's just focus on when. So I'm going to draw an example from my most recent book, published in the middle of the pandemic in 2020, Focus on When Alternatives Are Resolved. So in this book, I constructed a model of what I believe to be the smallest possible universe where you might be able to make a distinction between a deterministic version of this universe and a non-deterministic version. So here is a model of a tiny universe. You start out with nothing, and then you get what I call in the book the little bang. This is a tiny universe, and one of two possible beings comes into existence. And this being's existence is really extremely limited. The only thing, once this being comes into existence, it can either tick or tock, and then the universe comes to an end. So this is truly a tiny universe, and an observer of this universe would just see the little bang followed by either a tick or a tock. Now, I call this a deterministic universe because once the being comes into existence, it is preordained whether it will tick or tock. A model of the universe that is non-deterministic has the being coming into existence with the possibility still existing of it either ticking or talking. So those of you with a computer science background might recognize these models as automata, and they describe transitions in the state of the system. So these models make a fairly clear distinction between when the alternatives are resolved. In the deterministic universe, the alternatives are resolved earlier than in the non-deterministic universe. Now, in this book, I show that it is actually impossible to tell objectively by observation alone which of these scenarios is true. Now, this argument actually requires a bit of construction because when you're talking about universes by definition are all-encompassing. So I have to extend the universe a little bit in order to allow it to have an observer. So that we need more than one being, more than one automaton observing another. And within the universe, I show that it is not possible to objectively tell which of the two scenarios you have when the alternatives are made. You can't tell whether they're done earlier or later. And the argument follows from Robin Milner's notion of bisimulation relations between automata. Interestingly, it is possible to tell the difference with subjective first-person interaction. So if you're not restricted to just observing the system, but you can actually interact with the system, then it is possible to tell the difference, but curiously, not up to 100% confidence. So I refer you to this book if you would like to follow this argument, but it suggests that really the subtleties around determinism are really actually quite fundamental. However, if you're given the model, the difference is obvious. You can just look at these automata models, and once you've got the model, you can see when the alternatives are resolved. In this one labeled deterministic, they're clearly resolved earlier than in the one labeled non-deterministic. So one consequence of this observation is that if you think of determinism as a property of models, then it actually becomes much easier to reason about. So we can define determinism in a fairly straightforward way when we're talking about models. A model is deterministic if, given the initial state and the inputs, the model defines exactly one behavior. Now, the italicized and orange words here have to be defined in order to turn this into a formal definition. This is pretty easy to do in the context of automata models. We know how to define state, we know how to define inputs, and we know how to define the behavior of the model. For some models, it can be quite subtle, and your choices of how you define state, inputs, and behavior can lead to different conclusions about the determinism of the model. But the interesting thing about this is that you can come to very definitive conclusions about the determinism of a model, whereas coming to some definitive conclusion about the determinism of some physical system may be really much more difficult. So deterministic models have played a huge role in engineering practice. In fact, I would argue that they underlie the information technology revolution. Single-threaded imperative programs are a deterministic model. Ultimately, the physical system is just electrons sloshing around in silicon, and whether that physical system is actually deterministic is a rather difficult question to answer. We've figured out how to make silicon that behaves like the model with very high confidence, but it's never perfect. And consequently, the physical system will actually never match that deterministic model. An instruction set architecture is also a deterministic model. Synchronous digital logic, which underlies the construction of these kinds of systems, is a deterministic model. So these deterministic models have proved unbelievably valuable in engineering. So let me talk about the value of deterministic models. So one key property that deterministic models have is repeatability. Given the same inputs, you get the same behavior. This concept is essential to most of what we think of as testing. When you test a system, give it some inputs, and you get a behavior, then you expect it to behave that way when it's given the same inputs in the field. And if you can't assume that it will do that, then testing is not very valuable. So I'd like to cite one example of where a system proved to be untestable because of a non-deterministic approach to software development. So you may know that a few years ago, there were a number of incidents where Toyota vehicles appeared to have unintended acceleration out of the control of the driver. And NASA was commissioned by the US Department of Transportation to study Toyota software, and they were unable to find a smoking gun that could cause this unintended acceleration, but their conclusion was that the Toyota software was untestable. And one of the reasons that the software was untestable is that it used a principle that is very natural to control system engineers, which is that a control system always wants to read the most recent value of some sensor or some variable. And as a consequence, the software was written as a collection of concurrent pieces of code, all of which were reading the most recent value of a sensor or the most recent value of each other's state. And the software is, as a consequence, non-deterministic, and the number of possible behaviors given the same input is truly huge. So this software couldn't be tested using standard software engineering techniques like regression tests. Another value of deterministic models is consensus. You can have independent agents that will agree on the behavior of a system given some inputs. So when I balance my checkbook, my kids tell me that that's a silly thing to do these days, but I do it nonetheless. Every month I check to see whether my bank made any errors, and my conclusion generally is they didn't make any errors. In fact, me and the bank agree on what the bank balance should be given a set of transactions, and this is because the model that we have for what the bank is doing with my money is in fact a deterministic model. Predictability. Now, it turns out that some deterministic models are predictable, but not all. So one of my favorite illustrations of the unpredictability of deterministic models is due to my colleague Ted Lewis and McGregor, who published in 2006 a beautiful thought experiment where they looked at a simple physical system with two spheres colliding and a very simple Newtonian model of the dynamics of this system. And they asked the question, well, what was the precision that was required with which they needed to know the initial conditions in order to be able to predict the behavior of the collisions of these spheres? Then they assumed that once they derived the precision that was needed as a function of how far into the future they wanted to predict, then they assumed that they would measure the positions of these spheres optically, and then they derived the required wavelength of light that would be required to measure the positions of these spheres. They discovered that if they wanted to predict the positions of these spheres after 35 collisions, then a single photon of such light would have, to quote them, more energy than is currently posited for the entire universe in order to resolve the initial state of the system with precision sufficient to predict its behavior after just 35 collisions. a single photon. So this says that the unpredictability of this deterministic system is really not just a practical matter. It's really quite fundamental. This system is, in fact, unpredictable despite its determinism. So this phenomenon has become well known. Edward Lorenz was a meteorologist, a meteorology professor at MIT, and he was a pioneer in weather prediction using computers. And he was very frustrated by the inability of the very sophisticated thermodynamic models that were used at the time to predict the weather more than a few days in advance. And he discovered that the phenomenon was not just a limitation of how this was being done on the computers, that in fact the phenomenon was a fundamental property of the models which exhibit chaotic behavior. And chaos is the phenomenon where an arbitrarily small perturbation in the initial conditions or the inputs to a model can have arbitrarily big effects in the future behavior of the model. So many models of the physical world are chaotic, and hence, even though they're deterministic, they don't yield predictability. Fault detection is actually a property of deterministic models. When you have a very clear definition of what correct behavior is, then finding incorrect behaviors and recognizing them becomes much easier. So this is a little bit ironic because many people say that, well, you should use non-deterministic models because the real world is unpredictable. Well, that doesn't follow, actually. If correct behavior is well defined, you can detect the unpredictable results that occur in the physical world and then correct for them. Simplicity. You get one correct behavior for each input. This often makes systems much easier to understand. And unsurprising behavior. For many systems, you really want them to be boring. You want them to give you unsurprising behavior. Composability is another property of deterministic models. If your components' behavior is clear, your composition behavior is also clear. Now, many people, when I talk about this, automatically assume that I'm somehow dissing non-deterministic models. And many people get very defensive immediately because maybe they actually do a lot of their work with non-deterministic models. There is nothing that I have said that implies that non-deterministic models can't also be valuable. So let me go through some of the value propositions for non-deterministic models. One very simple one is abstraction. Non-deterministic models may be easier to understand because they may be much simpler than a corresponding deterministic model. So a sound abstraction admits more behaviors than the model that it is abstracting, and it may be much simpler, in fact. So abstraction and refinement are relations between models. So it is important to understand that these are relations between models. Okay? An abstraction of a model admits more behaviors than the thing it is abstracting. So every behavior of the thing that it is abstracting, the model that it is abstracting, is also a behavior of the abstraction. A refinement is the addition of detail to a model, which will typically constrain behaviors beyond what the model actually tells you is the requirements. Okay? So these are standard engineering practices. We use abstraction and refinement all the time, and non-deterministic abstractions of deterministic models could be extremely useful. Uncertainty about the world. You may not know something. You want to model something that's not fully understood. So, for example, if you're designing a self-driving car, you might want to model the human driver of the car. We don't, or at least I don't, understand humans, and therefore a non-deterministic model of the behavior of the human might be a perfectly reasonable thing to do. There's another kind of uncertainty, however, that also plays a role and can result in valuable non-deterministic models, which is uncertainty about your design. You may want to defer design decisions. So, for example, when you build software, you don't necessarily initially want to be concerned about the execution time of some particular piece of software. It's only later when you map that software onto a particular microprocessor that will become an important part of your design. So deferring design decisions is another form of uncertainty where non-deterministic models could be useful. Now, in my earlier book, published in 2017, Plato and the Nerd, I look very deeply at this relationship between these two kinds of models. And I identify these models as being models that are pertinent to science and models that are pertinent to engineering. So scientific models are models where it's incumbent on the model to match the thing in itself, the physical thing being modeled. Whereas in engineering, the thing in itself, it is incumbent on the thing in itself to match the model. So the goal of engineering is to create things that match models, whereas the goal of science is to create models that match things. These are mirror images of one another. And I'm not trying to create a taxonomy of the people involved, okay? Every engineer uses scientific models, and every scientist, or at least experimental scientists, uses engineering models. So, but the distinction between the models is really quite important, and confusing these two kinds of models can lead to some very erroneous reasoning about systems. So in a truly audacious slide here, I'd like to point out that abstraction and refinement are fundamentally mathematical concepts. They're relationships between models, not relationships between models and physical things. The relationships between models and physical things are science and engineering. And of course, mathematics plays an enormous role in science and engineering, but it is important to recognize that the mathematics is always about a relationship between models and not about a relationship between models and things. So you may know the famous quote from George Box, who says, essentially all models are wrong, but some are useful. It dawned on me, and it's embarrassing how long it took me to realize this, that George Box was talking about scientific models here, where it's incumbent on the model to match the thing. There's a mirror image statement that applies to engineering models, which is essentially all system implementations are wrong, but some are useful. The thing that you build, the piece of silicon, will never perfectly match your model. It always has the possibility of behaving in ways that your model did not specify. That's simply a fact about the world. But nevertheless, some of these system implementations are useful. So these two kinds of uncertainty are about scientific models or engineering models. Security is also another context in which non-deterministic models can be very useful. Unpredictability can be good, and some deterministic models are predictable, not all. And one way to achieve unpredictability is to use non-deterministic models, in which case you're assured of unpredictability. You also might have don't care conditions. Many behaviors are okay for the same input. That might be actually a flaw in your modeling technique. You might be using the wrong model, but nevertheless, sometimes it is useful to use models this way. Another context in which non-determinism can be useful is where boring is bad. If you're trying to create, for example, computer-driven musical improvisation, having perfectly predictable behavior is probably not going to yield a very good result. So the context of my work is on cyber-physical systems, where computations interact over networks and through physical plants, using sensors and actuators to interact with the physical plant. These create actually a huge modeling challenge because the components in this system use very different kinds of models in practice. We have developed very sophisticated engineering techniques for each of the components in such a composition, but these models are actually quite different from one another. So let's focus on the role of time. So time in a physical plant is very often modeled using Newtonian time. Occasionally in engineering systems, you actually have to use relativistic models of time, such as if you're designing GPS satellites. But usually Newtonian models of time, certainly if you're doing mechanical systems, a Newtonian model of time is a pretty good one. And in the Newtonian model, time is a continuum that advances uniformly everywhere in the system. But time is not like that in computation. In fact, the standard way of dealing with temporal behavior is sequences in computational platforms. In networks, we often use models that are discrete event models, where we think of events occurring in the network at points in time, but the network by nature is distributed. And so that model of time is not necessarily a perfect match with the Newtonian model of time that's used in the physical plant. In particular, the time that's available to us in a network is not advancing uniformly everywhere. And that model of time is simply inaccessible to any engineering model of a network. So in the physical world, time is actually a rather difficult topic, just like determinism is a difficult topic. Richard Muller, the physicist Richard Muller, published this beautiful book in 2016 all about the physics of time. And in this book, he describes a theory of time that he admits is probably untestable. He says it's going to require some black holes to collide somewhere near us to test this theory of time. Carlo Rovelli, in 2018, published another entire book on the physical nature of time and says right in the preface that the nature of time is perhaps the biggest remaining mystery. So how can we deal with this difficulty of timing in the physical world? Well, one way to approach this is the same way that I'm approaching the problem of determinism. Do we really care what the physical nature of time is, or are we interested in building engineering models that use a model of time? So put crisply, is our goal for our models to accurately reflect the timing of the implementation? Or is our goal for the implementation to accurately reflect the timing of the model? In other words, is the model a scientific model or an engineering model? If it's an engineering model, then we can have deterministic timing. And that proves to be, in fact, extremely practical, extremely useful, because we are able to build systems where they do, in fact, with very high confidence, reflect the timing of the model. Witness synchronous digital logic. It's a model ultimately of electrons sloshing around in silicon, but it turns out that we can build silicon that matches the timing in the model quite accurately. So if we're talking about a model of time, what are desirable properties? Well, a present that separates past and future, support for causality. So in other words, if A causes B, event A causes event B, then we would like in the model of time for A to occur at least no later than B. We need a well-defined observer so that we can define what the observer sees about time, and a notion of simultaneity, which is tied in with this notion of a present that separates past and future. And it turns out that all four of these concepts are problematic in scientific models, but are extremely common in engineering models and really quite useful in engineering models. So when we're looking at cyber-physical systems, the goal is for the implementation to accurately reflect the timing of the model, not for the model to accurately reflect the timing of the implementation. So I'd like to contrast this with what common practice is, for example, in the area of real-time software, where people worry about analyzing the worst-case execution time of some particular piece of software on some microprocessor executing at some clock rate. They're doing scientific modeling. If, on the other hand, you turn the problem around and your program specifies what the timing behavior needs to be in the computation, then synthesizing a realization of that is actually often quite easy. That a realization that will very accurately meet those timing requirements. So the question is, what should the model be that has those kinds of properties? So this takes me to my most recent manifestation of my obsession with determinism, which is a Lingua Franca project. This is a international collaboration. Most of the contributors are either in Germany or in the US. We're working with people at the Technical University of Dresden and Kiel University in Germany. And in the US, it's mostly people in Dallas and in Berkeley. And the project started in Berkeley and has grown to be a pretty significant collaborative open source effort. So Lingua Franca is what we call a polyglot meta-language. It's actually a coordination language. It's not a programming language. You can't build complete programs in Lingua Franca alone. You have to choose a target language. So here's a little snapshot of some of the people who are involved in this project, just taken as a screen image from a recent call where we were looking at particular pieces of code associated with the code generator. And here is an image from the Eclipse-based IDE that we've built for this system, which has this beautiful interactive visualization that was constructed by our colleagues in Kiel in Reinhard van Hanksladen's group. So the idea in Lingua Franca is that you specify components, software components that we call reactors, and reactors have a collection of reactions, and they have local state. And the reactions react to events. So on the screen here at the top, you can see a reaction to a shutdown event. So when the program shuts down, the chunk of code in this reaction will be executed. The chunk of code itself is not written in Lingua Franca. It's written in a target language. And in this case, the target language is C. As of this moment, Lingua Franca supports four and a half target languages. It supports C, C++, TypeScript, which is a dialect of JavaScript, and Python. There's also very nice progress being led by the Dresden team to develop a Rust target for Lingua Franca. So the delimiters with the curly brace and equal sign that you see on this image separate the target language code from the Lingua Franca code. So the body of this shutdown reaction is C code that uses some built-in infrastructure that is provided by the Lingua Franca code generator. So when you construct a Lingua Franca program this way, the code generator translates this into a standalone C program that you can then execute on any compliant platform. So built into Lingua Franca is a notion of logical time. So we can see, for example, a timer in this particular piece of code, which in the interactive visualization gets rendered as a little clock. And this timer specifies a 0 offset, which means that the timer will begin at the program startup time, and then a 100 millisecond period. And the important thing to recognize is that this is a logical notion of time. So even in a distributed system that is interacting across networks, if there are any two timers anywhere in the system that have these same parameters, 0 and 100 milliseconds, then the events produced by these timers are logically simultaneous. And every consequence of these events will result in a deterministic behavior that is driven by the simultaneity of these timer events, even in a distributed system. So you can have varying time intervals that can be calculated by your code as well, using this notion of logical actions. So the particular piece of code that I just showed you can be executed, and this particular piece of code reports two distinct views of time. One is the logical time, and the other is the physical time. So these are reported in nanoseconds. So you can see that these are, let's see, I think 50 microseconds apart. Is that right? 50 milliseconds apart. Okay? And you can see that the physical time is lagging behind logical time by about on the order of 100 microseconds on this particular platform. Okay, so this distinct notion of two timelines one of which is very precise. It's a logical time that is the model of the program, and then there's a best effort mechanism for aligning that with physical time. And this best effort mechanism makes use of standard real-time programming techniques such as earliest deadline first scheduling and so forth. You can have external asynchronous events, and the way that these work in Lingua Franca is using a construct that we call a physical action. And this physical action is depicted with this little triangle with a P in it in the graphical rendition of the program. And what this means is some external event, for example, driven by an interrupt service routine or an incoming message or a callback function or something of that nature, some external event that occurs results in a call to a built-in schedule function, which then assigns a logical time to this event based on a local measurement of physical time. So it uses your local clock, assigns a timestamp to this event, and then launches that event into the system. Once the timestamp is assigned, the entire behavior of the system is deterministic. You can specify deadlines, and those will be respected to the extent possible on the execution platform. And this illustrates that, but I'll skip over the details because I'm trying to keep this relatively short. You can also construct federated programs where now instead of a single standalone C program being generated by the code generator, you get a set of programs that can be executed on multiple platforms that will communicate over networks, and the communication fabric and the coordination that respects logical time is automatically generated. Now, we've learned a lot about how to coordinate given a deterministic model and a logical notion of time. And we've discovered that there are actually very distinct methods that have different properties and advantages and disadvantages. And we've built two distinct coordination mechanisms, one of which is, we call it centralized, and the other one of which is decentralized. These terms are a little oversimplified because it's not quite as clear a split between centralization and decentralized, but these are the names that we use for these mechanisms. So the centralized mechanism enforces deterministic semantics regardless of network delays and execution times. So the logical notion of time will be met. If there are failures in the system or failures in the network, then progress is blocked rather than yielding results that would deviate from the semantics of the program. That's a choice. The decentralized mechanism enforces forward progress. So progress does not get blocked in the event of failures in the network. The program continues to execute, and reactors will continue to execute the events that are made available to them. But then faults, where events occur out of timestamp order, get detected, and your program can handle those deviations, those violations of the deterministic semantics. So in particular, under both of these mechanisms, there are clearly stated assumptions about the execution platform. Remember that every system implementation is wrong, but some are useful. Every system implementation is guaranteed to be able to deviate from your model. That is an unavoidable fact about the world. One of the beauties of Lingua Franca is that the assumptions that you make that result in no deviation from that model are explicit. You give deadlines, and then whether those deadlines are met, well, they have to be met for the deterministic model to be respected. Well, they have to be met for the deterministic model to be respected, but in order for them to be met, you may have to do worst case execution time analysis and schedulability analysis on a particular implementation platform. Now, for federated execution, if you use the centralized coordinator, then the only assumption is reliable in-order network. So TCP/IP is sufficient to realize this. In decentralized, there are more assumptions. You have to assume bounds on network latencies and bounds on clock synchronization error in order for the federated execution under decentralized coordination to behave like the deterministic model. So I'd like to contrast this with commonly used techniques such as publish and subscribe, used, for example, in the robot operating system, and MQTT, which is very widely used in Internet of Things applications. Publish and subscribe is a non-deterministic fabric. It has no notion of logical time. Order of message delivery is arbitrary and dependent on network behavior, and it's possible to build programs that are reliable using this, but the model is non-deterministic, and consequently, these programs are actually untestable. Actor models, such as you find in Akka or in Ray, are also non-deterministic. There's no semantics to the ordering of models. Shared memory models and service-oriented architectures based on remote procedure calls also result in non-deterministic models, and my claim is that such models are in fact untestable and therefore really should not be used in any kind of safety-critical system. So in summary, this distinction between scientific models and engineering models is really important. In science, the value of a model lies in how well its behavior matches that of a physical system, whereas in engineering, the value of a physical system lies in how well its behavior matches that of the model. And another way to think about this is a scientist asks, can I make a model for this thing? Whereas an engineer asks, can I make a thing for this model? A Lingua Franca program is an engineering model, so its value depends on the ability of the physical system to match the model. Now, I want to close by pointing out that determinism is valuable, yes, but it certainly has its limits. I'd like to focus on one, incompleteness. So in 2016, in the very first issue of the ACM Transactions on Cyber-Physical Systems, Volume 1, Number 1, I published a paper on the fundamental limits of cyber-physical system modeling. And in that paper, I show that any set of deterministic models that's rich enough to encompass Newton's laws and also allows discrete transitions is incomplete. This is a metric space property. It's actually more fundamentally a topological space property. It means that the set of models does not include its own limit points. So a consequence of this is that non-determinism is unavoidable. So if non-determinism is unavoidable, shouldn't we just embrace it and forget about constructing deterministic models? Let's just construct non-deterministic models. Well, this is a specious argument. Death is unavoidable, but you may want to try to avoid it anyway. So for cyber-physical systems, we need to change the question. The question is not whether deterministic models can describe the behavior of cyber-physical systems. The question is whether we can build cyber-physical systems whose behavior matches that of a deterministic model. That's a different question. What about resilience, adaptability? Well, deterministic models don't eliminate the need for robust, fault-tolerant designs. In fact, they enable such designs because they make it much clearer what it means to have a fault. So these are the references. I thank you very much, and we'll close here.